I'm going to continue talking uh, about part two, even though there was no submission requirement for part two, but uh, it's it was about obtaining the dataset, CIFAR 10 dataset from the link provided in Canvas. I'm going to talk about the details of the dataset a little bit. So the CIFAR 10 dataset consists of a total of 60,000 colored images. The image size for each image is 32 by 32 pixels, and the total number of classes in the dataset consists of 10. So basically 6,000 images per class. All the images are distributed evenly among the classes. Out of these 60,000, 50,000 images are for training sample and 10,000 images are for testing sample. And these are also individually equally divided among the training and test samples for each classes, which means that 5,000 images for each class in the training sample and 1,000 images in the test sample for each class. And these are randomly picked images from each class for the training and testing sample. The classes in this dataset are entirely mutually exclusive, hence there is no overlap between two classes. And the names of these classes on the left you can see are airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. So this was a little bit of overview about the dataset before, which I think is important before we go on to part three. Part three, we had to build, train, and test a convolution neural network on the CIFAR 10 dataset. I'm going to talk about the design of the neural network first. This image highlights the design of the neural network. It consisted of 2 convolution layers, and then each convolution layer had a pooling layer with it after that, and then 3 fully connected layers in the end. The first one is the normal feed-forward fully connected layer, which we can also say dense layer. The second one is a fully connected neural network layer with dropout. And the third one is for the output layer, basically. I have the critical information here regarding each of the layers we have. The first one, I'll talk about the first one, convolution layer 1. Each convolution layer has a shape of a 4-dimensional structure. With the first dimension is the batch, the second is the height of the image, the third is the width of the image, and the fourth is the depth. So we have 1, 32, 32, and 32 here. So the input shape is 32 by 32, which is basically the image size. And then 3 is representing the number of colors, red, green, blue, since this is a colored image, as opposed to it was 1 before we've seen with the mist data, since those were grayscale images. And then in output, we will extract, the image size would be the same, but we will extract 32 features out of this image. And the window size would be 5 by 5. So hence the filter shape would be 5, 5, 32, which is the input and input features, and 3, which is the input features, and 32, which will be the output feature. The stride will be 1, and then the stride shape will be 1, 1, 1, and 1. The padding will be same. We do not need to have any padding. And then the activation function is ReLU. I would like to mention here that each convolution layer has an activation function, but this function has its own layer as well, which comes right after the convolution layer. The purpose of this layer is not to put any filter on the data, but only extract and learn features. And the input and output remains the same during this layer. So we have 32 by 32 by 32 here, as it came from the output of the convolution layer 1. And then this output goes ahead to pooling layer, where we have the pooling method max pooling. The window size is 2 by 2. The window shape is 1, 2, 2, 1. The stride is 2. Stride shape is 1, 2, 2, 1. The padding is same. We do not need any padding. And the input and output channels also remain the same. One, which is 32. One thing we need to, I would like to highlight here, that the pooling layer transforms the shape of the image, and it reduces the size of the image in exactly half. So if you can see here, the input shape is 32 by 32 by 32, but the output now is 16 by 16 by 32. And then now this output will be the input of the next convolution layer, as you can see here. And then the output, in the output, it will double the features extracted from previous, which will be now 64. And then the rest of the information is pretty much same as convolution layer 1. And similarly, ReLU layer here with the convolution layer, which will have its input as 16 by 16 by 64. And then this will be an input of the pooling layer 2, where we have the same pooling method and pretty much all the same information. And if you notice here again, that the size of the image reduces to half again, from 16 by 16 to 8 by 8. Now this output will be flattened and fed into the fully connected layer 1. And the input channels for this layer are 8 by 8 by 64. And the output channels are 1024. The next layer we have is the dropout layer, which will have its input and output channels as 1024. And then finally, this dropout layer is basically to remove any bias from the data. And then finally, we have the final output layer, which will have its input channels as 1024. And output channels are 10, since we have 10 classes. This is pretty much all the critical information about the neural network. Now I would like to talk about a little bit about the code and the results of the process. First, I would like to talk a little bit about the code part. And this initial code was provided by Professor to prepare the data to feed into the convolution neural network. In which the images are also reshaped for us so that we don't have to worry about that. And it can be directly fed into the convolution neural network. These are the supporting functions for building all the layers. And then here we are creating our neural network layers. Convolution layer 1, then pooling layer, then convolution layer 2, then pooling layer 2. And then here we flatten the outputs of the pooling layer in order to feed into the fully connected neural network layer 1 with output size 1024. Then we apply the dropout here. with the last layer being the output layer. And we've used softmax as a loss function and Adam optimizer for optimization. And we have our model ready here. The steps performed will be 5,000. This is an additional step I've done. I'm saving the results of the testing part into a data frame so that I can export into CSV, which I can use to compare with homework 4, which is a requirement of part 4. We'll come back to that later. So this is basically the training process, and on every 100 step in the training process, we test the accuracy of the model to see how it's performing, and then print out the accuracies here. I'm going to talk about the results on about this model a little bit. The highest accuracy level, as you can see, obtained at the end of the training basically was 67.4%, but this was not the highest accuracy level actually. The highest one throughout the training process was 68.62%, which was obtained after 4,100 steps of training. And it kept on increasing until this point, but later on it decreased a little bit down to 67.4%. So although the accuracy level is not too high, but considering that these are colored images, it's not too bad either.